Okay, so now we are resuming the demonstration using MATLAB Live, and it will be a Gabor demo. Maybe I call it it's a live script. Now, the short explanation of Gabor, our short-time Fourier transform time frequency analysis, is we're doing all the things that we are able to do with time frequency shifts. And one of the important ingredients, is to use a Gauss function, just because it's such a nice thing. And we want to verify that this Gauss function is really up to scaling invariant under the Fourier transform. So there is actually no eigenvector for the discrete Fourier transform if you don't normalize it properly. So maybe I'm showing you the unitary version of this is FFTU. It's just FFT divided by square root of n, and F2 spec G, and maybe I'm taking G to the power pointwise to the power I don't know 8, and then I run this. Then you should be able to see a few things. First of all, that the norm of the Fourier transform of the discrete Gauss function is square root of n, and you can verify this easily, times the original one. If you do the unitary version, you build this into the routine and everything is fine. Then if you compare it, you see that a higher power of the Gauss function is, first of all, a different scale, but it's much more narrow, and which makes the function more wide on the Fourier transform side. And so if you want to understand the Fourier transform, but it's for the continuous Fourier transform, I would recommend to use GeoGebra and to say we define the Gauss function. Actually, we have a command. I'm going to this other window now. This is just the home command, and recall that we can define a function by a command which gives it as a function of the argument, and then we can plot dilated Gauss functions using the arithmetic progression, but this is not the point. Okay, now I want to recall also, maybe as doing session, if you do F23 spec, I'm doing now showing a Gauss function, a rotated Gauss function may be shifted in a cyclic way by 20. Or I do a rotation and a modulation, and in order to show the pure effect of modulation, I'm doing 0 shift and a time modulation with frequency 12, which really means maybe I should do this first and show the outcome. So F3 spec is of course showing 3 functions and their Fourier transforms, their spectra. So it comes up here. So you see the Gauss function is invariant, but shifting the function is multiplying by the Fourier transform. Just again, this is a well-known formula, but also trivial formula, because what is happening if you have the sequence 1, 2, 3, 0, 0, 0? You would say, oh, it's 123,000. So everything is multiplied by 1,000. So now you have a polynomial, and instead of taking 1 x squared plus 2x plus 3, you're multiplying everything by x to the 3rd power. And that means, of course, that you're just taking the function set to the 3rd at the unit roots of order n, but this is exactly this pure frequency. So it's translation in the cyclic sense goes to modulation, and due to the symmetry, you can argue modulation has to go into translation, but sometimes you have to be careful because there is a minus direction in the one thing. So if you multiply with the pure frequency, then you're shifting, and you can also check, maybe this is a different thing here, that rot mode. Yeah, maybe we try to verify that we take a random vector rand cn of 1 and n. So you see I'm working with the row vector now. We verify that this row vector is normalized. So this is why the command is called random complex normalized. And then we say, what if we want to compare this vector in a rot mode sense? So I'm not rotating, but I'm modulating by 12. Now the question is, modulating by 12 means we are multiplying with a pure frequency which has 12 oscillations. And let me say I don't want to check technical details, but see the advantage of this experimental setting. I would like to check what happens, whether this is the column minus 12 or plus 12, so to say. So I'm just multiplying with row. Well, maybe I take, yeah, maybe I take row. Yeah, because we have, otherwise we have a strange effect. So I'm multiplying with a row vector and want to see whether this is okay. Okay, and you see it's not okay. So I leave it here. And I'm copying this command. And I'm doing this, but remember, when we are looking at the tail of the Fourier matrix, the last column has one oscillation. So if we take n minus 12, I think that should work. It's 12 or 11, I'm lazy now. We see, so it's still not okay. So I have, yeah, okay, of course, because n is one oscillation, n minus 3 is, okay, that's, now I'm a bit confused. So let me see, what if maybe it's because it took rows. Okay. Yeah, okay, so I don't know what's wrong here, but instead of playing around too much, it's clear from the picture that I'm multiplying with some function. And I would say maybe the last trivial command is, if I do a rot mod of xx by 0 and 0, I do not do any shift, then of course I should get back my vector x. Yeah, and this is definitely okay. And I can also try to say TF is the time frequency rotation matrix of size n and 3 and 5. And if I'm not lost too much, I would expect that the application of this matrix, and since we're in the row mode, I have to do right matrix multiplication, should have the same effect. So kind of this is where we see the operator, and now I'm doing the action of the operator in a much more direct way, rot mod xx and 3 and 5. Also to check whether the order is done in an appropriate way. And just a moment. Oops, 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 oops. Okay, so let me check whether I'm in my row mode. Maybe that's the obstacle row. So row column mode is telling me, oh yeah, that's maybe the problem. I have the commands row column mode to show me what my row column mode is, and that was somehow switching to column mode. So if I put row column mode to columns, I'm putting it actively into column modes, but I'm used to do row column mode rows. So this is just setting everything. And now maybe we can do this paragraph once more and see. It doesn't look much better, except in the last part we have now a correct result. We see that if I apply the operator, and it's supposed to be a matrix acting from the right on the row vectors, then it's the same as having the rotmod command. Now, the next command I would show you is the lattice point. If I want to create a lattice points with, okay, I have to define the N and the A and the B. Okay, I remind you that N is 480, my standard A is 20, and B is 16. So everybody can see that these are divisors. And then I'm doing I do a representation of this using this spice command, but using it in the starting a new section, doing it in a centered way. Okay, sorry, no, it's not good. It should be say spice, but I do image C. So I'm doing this once more. Maybe I'm doing an axis on top of this. So if I represent this, it tells me maybe N over A, N over B. It tells me a few things. First of all, you see a grid of points, and N over 20 is clearly the product. 20 times 24 is 480. So if I jump to the right by 20, so actually in MATLAB, I have to jump from column number 1 to column number 1 plus 20 is 21, 41, 61, and so on. And if you ask me what is row number 441, I would say, okay, 440 is N minus 20. So it must be the second last column. So these are the indices or so. Now, if I do something harmless, if I do, I don't know, random is, I take a random matrix and I want to have random points now. So I do random N, and this is between 0 and 1. And now I'm choosing, so random N, and I'm taking a 0, 1 matrix, which says if I'm larger than 0.997, then it's okay. So I'm now showing you all the positions where my random matrix was larger than this threshold, close to 1. So it's 3 per mil of the dots are expected to be positive. Then products. Maybe I'm leaving the old figure and running. And then you see here, okay, it's not so bad. What you also see in the plot here, I'm getting 720 plots. And this is because locally I'm jumping by 20, which means I'm getting 24 positions in the horizontal direction, so 24 columns. Now in each column I'm jumping by 16. The complementary divisor is 30, and therefore I'm getting 30 points per column, and the product of those two numbers is of course 720. And by taking this threshold, I was getting, with kind of good luck, 726 points. So they're just spread out irregular. Now, if I want to have ND regular, is find lum, then it tells me which are the MATLAB coordinates, lum, and the here is find random. So the coordinates of the random vectors. You would get a sequence of coordinates which are is quite long. So let me just show you the first, I don't know, 4 or 5 of them. And the same for the irregular one, and the irregular 1 to 5. And if I show this to you, you will see certain indices. And the first one is quite clear. We are going where our lattice, regular lattice starts, so to say, with 0, 0, which is the first MATLAB coordinate column. And there you go down by 16. So it's clearly 1 plus 16 is 17, 32 plus 1 is 33, and so on. Now, in the irregular case, you are seeing the number 378. What does it mean? It means in this experiment, there was a single point in the first column. The labels of the first column are going from 1 to 480. And now we are having the first point. It looks as if the second point was in column number 2. Then maybe, I'm not sure, if you look at this, you can try to convert this. So there is a command, row call number, which I'm not ready. I will insert it in the maybe I can find it as a row call. Sorry, shouldn't be. Yeah, this. Yeah, I think it's the built-in command index to int to sub and sub to int. I don't want to play around, but clearly, if somebody is giving you a list of running labels, you can find which rows and columns these vectors are. Now the point is that even if you have such an irregular collection of points, then you are still having a natural order of these points. Now, what we will do when we are computing at once, so I'm doing a new section. If we take this random signal, which was XX, and I take now the capital STXX, I'm doing the STFT of this. And the first thing I'm showing you is what is the size of this ST and also how fast it's computed. The short time Fourier transform. Okay, it's of course a wrong symbol. So it's very quickly computed. It's an n by n thing. And if you want to see it now and with the then it will look as the following object. And this is quite, yeah, maybe I'm adding the plot.ax command. So this is what you can see all the time. Maybe you're generating a new one each time you call it. So let's take x-axis rand cn 1x, 1n, sorry. Don't want to see it. This was not my purpose. Just want to have this. So I'm running it now. I'm computing a new random signal, and I show you the corresponding. It always has this pattern. And there are some blue dots, and it turns out that these blue dots are more or less the areas where I can do a color bar, are where the absolute value, actually what I'm doing is I'm plotting, that's something I should tell you. I'm not plotting the real and imaginary part, but I'm plotting the absolute value of the short time Fourier transform. Sometimes it might be better to show you the spectrogram, which is absolute value squared, but maybe I'm doing this in the color bar, of course. maybe I'm doing this. I'm doing the absolute value squared, and because my routine is taking automatically, no, I don't have a problem with the keyboard. Okay, so I'm showing it once more. That these blue dots are more or less the area where the short-term Fourier transform has a 0. And it's interesting to observe that if you start counting this and playing around, these are more or less n points, and they're regularly distributed. So they're a little bit clustered somewhere, a little bit further away. But this is would be another way of creating n random dots in the plane. But of course, determining the zeros of a complex valued function is also not so easy. And Imri STXX. So maybe I'm doing Imri. Sorry. STFT G with G. So I want to show you another thing now also. So the comp imri command is, of course, a comparison. Compare, please compare. Show me two spectrograms, one from my random function and one from the Gauss function. So in each case, the window is this. And what you see here is the real part and the imaginary part, and you see that they're having high oscillations. Whereas here in this part, the Gauss function is sitting at the center, so it's not it's highly concentrated. So let me do another experiment. Section break. So what is show me the STFT of rod mod of G and 40 and 100. Now this is a highly oscillating, somewhat shifted Gauss function, and we would like to see maybe sorry, the keyboard. Show graphic is just put it on display. I think that's not relevant here. But what you will see here, or supposed to see here in a moment, is that the spectrogram of a Gauss function is yeah, I didn't do a new figure, so I did a figure is something well concentrated, but now I'm a bit puzzled. Why is the rod mode not showing any effect? Because this is looks like the I'm just doing it once more. Okay, maybe yeah, it's because of my convention. I was using the column mode, and if you do a cyclic rotation of a column vector along the rows, you don't change it anymore. That's why nothing has happened. So I'm redoing it. Gauss G is Gauss function of size n. And since meanwhile I'm in the row mode, so you see it has Gauss and K, sorry. Also some disadvantages, of course, to have two modes. Yeah, now everything should work. Yeah, and you see it has been moved by 140 pixels to the right. So it's a little bit more to the right and a little bit into the positive direction. And now one has to choose a convention, and the convention was, of course, we are working with matrices, and they have rows number 1 to 3. Therefore, going to higher row numbers is the same in the picture as going down, which is interpreted as going to higher frequencies. So to multiply with the columns of the Fourier matrix, and the only thing I have to check is which is the order. Okay, so now the next command is, if somebody is giving me a collection of points, maybe the irregular one or the regular one, and each of these dots has coordinates. It corresponds to a certain right and downshift compared to the left upper corner. So you can say each dot can be viewed as an operator. And therefore, if you have 720 points, you can take the Gauss function, choose one point after the other, and you can create a family. So that's what we will do next. And that's a standard command, of course. So there are two commands. G is GAP-BASP, and the P stands for product. I'm starting with AB. And there's another command, G1 is GAP-BAS of G and LAM. And we will do GRD is GAP-BAS of G and RD. RD. What is the size of these things that I have created? G1, size of G, size of GRD. You see, since I'm using row vectors, each signal that you find in this collection is a vector of this form. And the first two have the same format, because when the input is a 0-1 matrix, which was representing our lattice, I'm just going through these points in the natural order. And the GAP-BASP command is only a fast way of doing this. So let's verify what is the difference between the G and the G1, and it should be 0. It should be really the same. Now, it may be not 0 because, yeah, so what does it show you? It's numerically the same, but not in the sense of computed in identical way. And the way is very simple. In the first command, you're just saying, well, I create a collection of, we have in each column 30 frequencies. So we create a copy with 30 shifted versions of our Gauss function at that particular position, put them into a matrix and multiply them with all the 30 selected frequencies. And then we go to the next block and we use the same frequencies. So whereas here we have 24 blocks, each of them giving 30, and we compute 30 of them at one stroke. In the GAP-BAS command, we're just saying, well, you're giving me a bunch of points, and for each point I compute row and column numbers of the one, and I do a rot mod command on these things. And of course, this is slower. And you have seen now the RD has changed. We have 672 elements or so. And therefore, it's also interesting maybe to say what is the rank of G, and what is the rank of GRD? So are the vectors that we get a generating system? And the answer is satisfactory. Okay, it's great. There are enough building blocks even with this randomly generated thing, but it might be also interesting to say what are the relative costs. So how big are the coefficients, or what is the range of the coefficients GRD that you might have. So some vectors might be easy and cheap to compute, others might be different. And you see, I would say the condition number is in the order of 4,000, 10 to the third. So it's not so bad, but still it's not easy and not so nice to compute it. Now the way to restore it, the function from the short time Fourier transform is usually in frame theory. You're saying, well, we have now the synthesis operator. So if somebody is giving you a signal or he has synthesized it, you would like to synthesize with these things. So if you say my matrix with 720 row vectors is representing a generating system, the synthesis operator should be okay. But we have many more vectors. We have redundancy. Maybe I'm showing also this. The redundancy, the redundancy in this window. The redundancy is, well, I have, how many vectors do we have? We have n over a times n over b compared to the dimension of our space. And of course, we should compute it as n over a times b. And in our case, this is just the quotient between, this is a typo, b. It's the quotient between the number of building blocks related to the dimension of the space. So it's a multiplicative term. So it's 3 over 2. And therefore, we can have a lot of representations. And therefore, the best way to compute the cheapest representation is to use the pseudo-inverse. I will talk more about the pseudo-inverse in the linear algebra session next time. Maybe not next time, but at some point, because now I want to really jump deeper into Gabor analysis. But we can do it now with the pseudo-inverse command. So the GD is the pinv of G, and I do a prime here, because now this means that maybe verifying this something quite obvious mathematically, but experimental wise it's maybe easier. I do the pinv of G and put the prime conjugate to the outside. You remember we have complex valued functions now, so the prime is really conjugation. And so section break and run this section. So these two things are really the same, but now we want to see the entries which this family has. So just to tell you, the format size of GD, because we were putting this transposition, is exactly the format of the original matrix. So we have another 720 elements. So it's 720. And now the claim is that if you're multiplying, in the case of a generating system, the pseudo-inverse with the matrix, and now we have to remind ourselves that we are doing this with the row vectors. So maybe I'm doing this command first. I'm saying, well, I claim I can recover this, the signal from the scalar products. So I'm getting, first of all, maybe I'm saying I'm doing this here. And then I'm doing synthesis with the row vectors. I claim that I'm recovering XX. So maybe I should go a bit slower now. But the first thing is just a simple experiment. This funny pseudo-inverse, you see, because I was putting the prime twice, one in order to generate a family of signals of the same number. So for each original signal, I have a dual element. And now I am computing what happens if I take the collection of scalar products with these 720 new vectors, which are kind of the rows of this pseudo-inverse. And I'm seeing that I'm getting some coefficients. And so, of course, what I would do is COF is XX with GD, and the size of these coefficients vectors is, of course, a row vector with 720 entries. The abstract theory of pseudo-inverse, or more Penrose inverse, tells you that I have computed the minimal normally square solution for the representation. And of course, again, the norm, I know it's representing everything, so I just really say the norm of X minus the coefficients used for as linear linear combination with the rows of my Gabor matrix. And then we'll see that everything is fine. So I have computed, first of all, evidence. I have computed some coefficients which allow us to do a representation of the given random vector. And the claim is it's the minimal norm pseudo-inverse. So maybe another experiment, which is not feasible now because we are running short of time, would be to say, well, let's synthesize a random vector by doing random coefficients first, of length 720, then computing these coefficients using the pseudo-inverse and verifying that the random coefficients are longer than the vector itself, which is quite plausible because we have a matrix which has a null space of dimension 720 minus 480. So it must be, well, the redundancy is 300, is 3/2, so it's 1/2, so it's 240. So the null space is 240 dimensional space. So a lot of the energy of the random coefficient that I would use would go here. Okay, now what is more important, which I really want to analyze now, is that this pseudo-inverse has a certain structure. So the first one is, because now the pseudo-inverse is matrix also having column row vector, sorry. I would like to show you my row vector. So maybe I'm saying figure guarantee. And you see it has, and of course I've chosen characteristic values here. It's a function which has two effects. One is, roughly speaking, it's around 0, but it has a tipping point, and it turns out to be something like a Gauss function divided by the square of a Gauss function near the origin. And on the other hand, it has side lobes or so. So this is the first observation. Now we could look at random. We could do another figure. And we could look at GD number, I don't know, 123, 4. Plot that one. And what we will see by inspecting all these elements, that they're actually having a structure which is quite similar to the original one, namely here we have again the same side lobe. Maybe it's not so visible here anymore. Maybe I don't take a larger number, or 21. Yeah, I don't know why it's not showing up. Okay, so you see here it's number 121. Maybe it's plausible because this is now what would be the element number 121 in our Gabor family? We would have number 1 would be a Gauss function. 30 points later, so it's 31, 61, 91, and then 121, you would have pure translates. So it's nice to see now, this is a pure translate of the original one, and it's translated by a certain amount. And now we can say, well, maybe we regenerate from this given element we take this gab-basp command, take gdab, recreate a family according to the same pattern with the same modulations, with the same shifts in the order coming from the natural interpretation of row and column numbers. And then it turns out that actually the dual of a regular Gabor family is a regular Gabor family. Now, just in order to show you some effect in the, maybe I'll leave it out. So in the case of the irregular Gabor family, we can find that the dual atoms are, if it's a nice and highly good, well-spread family, they are changing their shape completely, but they're still having the same localization in time and frequency. So this is another interesting command. Now, since I should come to an end now, I would like to just tell you that, of course, what we were doing here is to compute a dual Gabor family by doing a huge pseudo-inverse. So if you had larger dimension, so what we could do is we could say, well, we are taking the Gabor frame operator, which means we're applying to a row vector first a coefficient vector, which is multiplying with G prime, which maybe I'm just telling you that the size of the G of the matrix S, the standard name for the frame operator, is really n by n. It's a positive definite matrix, as you can check also. But now I want to tell you that if you would apply to this collection of row vectors, which we have called S, the inverse of S, or we have computed this with the pseudo inverse, this is really giving us the same result. So the standard theory of Gabor frames explains the situation in the following way. You have to determine the frame operator, which in my case is now the matrix S. And then you have to apply individually the inverse frame elements to all the elements of this family. And we can study and will study this further more. But what I would like to show you, at least at the very end, is that Vs, Ds are the eigenvalues of S. And it's, of course, instructive to study the eigenvalues. So Ds is diagonal of the Ds. So to look at the eigenvalues of this matrix, so figure plot Ds, because I find this is an unexplored property. I've seen a lot of these eigenvalues and they always look probably very similar like this. So maybe we put a grid on this. So they seem, this is for the case of discrete Gauss function, I have to say. They appear to have a shape which is symmetric with respect to this. So you see a jump here, which seems to be the same as the jump here, and after a while a jump here, and so on. And but we don't have any theory of this. So this is quite interesting. Of course, we have seen that our frame element is having a certain decent condition number. And if we look at these condition numbers, we will see that the condition number of the frame operator is the same as the square of the condition number of the G. That's more or less for a rectangular matrix the way how you compute it or so. But it's also the quotient of the B and the A and for Gabor frames. So it's more or less, it has to do with the biggest and largest eigenvalue of the frame operator. And I will probably next time show you a lot, some intuition about irregular Gabor families or so. So kind of what, in the regular case, it's a bit annoying. It's much more visible if you take irregular Gabor families like the one that we have now. And so what I want to do at the end is to indicate that we have a lot of dual ways to compute this GD in a direct way. The very old routine is, I'm not sure if I'm having it ready, Gab, Joel, Guido Janssen, GAB. I mean, we have several routines, at least 5 or so. I will just try these 2 here. These are direct ways of computing. Okay, so this command is not the right one. No. But maybe I'm just not remembering correctly the code name. But the point is, this gap dual is a way to compute. Yeah, okay, well, maybe I should skip this here. So maybe I should just say, if we compute now directly the dual, for example, for the case that we have 12 and 12. So what is happening if I do other divisors, other lattice constants, and that could be the last picture for now. How is the shape depending on the choice of our lattice? And you see, this looks much more decent. It has slightly negative parts, but it doesn't have a dip. And so the story would be, how can you save this to make sure that everything is restored? How can you make? How can you get an understanding? Okay, I have to do it later. An understanding of the change of the dual atom as a function of the lattice constants. So in the theoretical world, it's stored in the paper with Norbert Keiblinger, varying the lattice constants. So essentially it says that if I take similar lattice constants, then I will get similar dual windows, or I could use the dual computed for a slightly different lattice constant as a good approximate dual Gabor window. So how could I use it, such approximate dual? Well, you use it as a first approximation and then you iterate and so on and so on. So there are many ways of using this information, and I think I should stop here now. I will stop the recording.